NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hey, good evening, ladies and gentlemen. How's everyone tonight? Excellent. Hey, Jane. Well, anyway, thank you guys all so much for coming out tonight. Volcanoes have helped transform the surface of the Earth, the other terrestrial planets, and the Moon. However, the biggest volcanic eruptions in the solar system are taking place not on Earth, but on Io, a moon of Jupiter. This wonder of the solar system is a fascinating laboratory where powerful eruptions result from tidal heating. Despite multiple spacecraft visits and spectacular new observations with Earth-based telescopes, some of the biggest questions about Io's volcanism remain unanswered. Getting the answers requires a few things: understanding the difficulties of remote sensing of volcanic activity, innovating a new approach to instrument design, and ultimately returning to Io. Our guest tonight will describe how studying volcanoes on Earth leads to a clearer understanding of how Io's volcanoes work and how best to study them. Tonight's guest is a research scientist and volcanologist here at the Jet Propulsion Laboratory. He received a doctorate in volcanology from Lancaster University in the UK in 1988 and has been at JPL for over 20 years. He was a member of the Galileo NIMS team, is a co-investigator on the Europa Clipper Mapping Imaging Spectrometer for Europa, has written over 100 papers on observing and understanding volcanic processes, and is the author of Volcanism on Io, a comparison with Earth, published by the Cambridge University Press. He continues to be engaged in research into volcanic eruption processes, spacecraft mission and instrumentation development, and fieldwork on volcanoes around the world. He was also a co-recipient of the NASA Software of the Year Award for the Autonomous Sciencecraft Experiment, which successfully demonstrated science-driven full spacecraft autonomy. His love of volcanoes is truly undeniable. Every year, he sends his PhD advisor a birthday card depicting a work of great art improved with a volcano. Ladies and gentlemen, please help me welcome tonight's guest, Dr. Ashley Davis.
Thank you. Thank you all very much for coming. The surface of the Moon and the surfaces of the terrestrial planets have all been extensively modified by extreme volcanic activity in their distant pasts. And these large eruptions are mostly unknown in the manner in which they emplaced large, vast fields of lava. But there was one place in the solar system where such voluminous, powerful, extensive flows, volcanic eruptions are taking place, and that is the Jovian moon, Io. Io holds some fascinating views of how Earth might have erupted in its distant past, is a key to understanding the evolution of the large Jovian satellites, and is a great template for looking for volcanically active exoplanets. It's truly an amazing place to a volcanologist. I think I have a pretty cool job because I study volcanoes for NASA. And although this usually means that I spend most of my time staring at a computer screen and crunching data and looking at remote sensing observations of volcanic eruptions, occasionally they let me out to go and play on a real volcano somewhere. And it's a great job, it's very exciting, and it's taken me to the ends of the Earth. This is, in the background here, we have Mount Erebus. It is the world's most southerly active volcano in Antarctica. At the summit, there is a crater with a lava lake in it. This is in Ethiopia. And again, over on the right, we see another lava lake on a volcano called Erta Ale. Now, it's important to think about volcanoes and what they mean for the evolution of a planet. But apart from that, volcanic eruptions are an agent for change which can affect millions of people very quickly. This is Mount St. Helens erupting in 1980. And on Earth, over 250 million people live within 20 kilometers of a volcano that can erupt like this. Apart from that, moving away from the human element, volcanoes are a window into the interior of the Earth or any other planet. They are an indication of internal heating, which has melted the upper mantle, and they conveniently transport material from the inside of a planet to the surface where it can be observed with instruments on spacecraft. And there are many styles of volcanic activity on Earth, and I've been spending most of my time looking at low viscosity basalt-type eruptions at lava lakes. A lava lake is the top of a column of magma connected to a magma chamber. It's an open system around which magma circulates. And they're quite rare on Earth. They tend to crop up in quite extreme environments, although there is a big one in Hawaii now. But they're very useful for studying basaltic processes. And I've been studying these on Earth to better understand what's happening on Io. Now, the Galilean satellites were discovered by the great Italian astronomer Galileo Galilei on the 9th of January 1610. Galileo noted in his notebook that using this new Dutch invention, the telescope, he observed Jupiter and noted these little stars close to Jupiter, and noted that over the next few nights, the position of these dots would change, and came to the conclusion these were actually moons orbiting Jupiter. So we can jump forward 400 years to the Voyager spacecraft. There were two of these built here at JPL, and Voyager flew through the Jupiter system, and on Io made one of the greatest discoveries of planetary science. That Io had these large volcanic plumes. And this was a real revolution in our understanding of the outer solar system, because up to this point, it was generally thought that the moons of the outer solar system planets were small, dead worlds where over geological time, the geological processes that were changing them had basically been damped down into nothing. They were small, cold ice balls. But here we have Io being a dynamic, evolving world. The follow-up mission to Voyager was fittingly called Galileo, and I was on the Near-Infrared Mapping Spectrometer team, NIMS. And here we see in the lower right an observation of Io with NIMS. NIMS was an instrument that was particularly good at detecting the heat given off from volcanic eruptions, and sent back a lot of data. Now, the NIMS, the Galileo main antenna didn't open, and so there was a restriction on the amount of data that came back. And so there are still some gaps on Io that need to be filled in terms of coverage. So here we have the 4 large Galilean satellites as imaged by the imaging system on the Galileo spacecraft: Io, Europa, Ganymede, and Callisto. Io is closest to Jupiter, and Callisto is furthest away. And here we have Io, as seen by the camera system on the Galileo spacecraft. And the colors of Io's surface are diagnostic of composition. If it's yellow, it's rich in sulfur. White areas are rich in sulfur dioxide. But what's of great interest to me are the black areas and the red areas. The black areas are areas of silicate volcanism. This is where material like basalt is being erupted onto the surface. The red areas are thought to be short-chain sulfur allotropes, which are evidence of active or ongoing volcanic activity. So every black or red area in this image is an active or very recently active volcano. Now, the amazing thing about Io is that it's actually volcanic at all. Here we have Io next to the moon, and the moon was once very volcanic. These dark areas are the mare, and these are layers of basalt many kilometers thick. But the moon is, as far as we can tell, volcanically dead. And this is because what drove volcanism on the moon and what continues to drive volcanism on Earth is internal heating by the decay of radioisotopes. This is material that was incorporated into the planets and moons when they formed. Now, the laws of physics dictate that a small body loses heat faster than a large body does. So over billions of years, the moon and Mercury and Mars lost their internal heat to space. The heat that was driving this volcanological engine within each planet slowed down, and then eventually stopped, and large-scale volcanism on these bodies was still forever. So this is what happens with a small body with an internal source of energy. But with Io, something very different is happening. Io's source of energy, which drives its volcanism, is external. Io, Europa, and Ganymede are in an orbital resonance. For every orbit that Ganymede makes around Jupiter, Europa makes 2 orbits, and Io makes 4 orbits. So every time Io passes, for example, Europa, Io gets a little kick, and it's taken Io's orbit and changed it from a circular orbit into a slightly elliptical orbit with a bit more eccentric orbit. And Io gets twisted each time it passes one of the other 2 satellites. And it's this tidal flexing that generates heat within Io that manifests at the surface as active volcanism. So it's an external source driving this extraordinary level of volcanic activity on Io. It's an elegant cosmic ballet, if you like, choreographed by the immutable laws of physics. Now, just to put the majestic scale of Io's volcanism into some sort of context, this is the amount of material that is erupted from Earth's volcanoes every year. Most of this is erupted on the ocean floor at mid-ocean ridges. On Io, this is the amount of material that's erupted every year to erase any evidence of impact craters. There are no impact craters on Io, unlike any other solid body in the solar system. So there really is a truly astonishing amount of volcanic activity taking place. Over the years, we've collected a lot of data from spacecraft, and this is a mosaic compiled from the best Voyager and Galileo spacecraft data. And basically, we've covered most of Io at resolutions good enough to identify volcanoes from their appearance and their thermal emission. And to this has been added a growing data set, an astonishing library of observations obtained with large telescopes based here on Earth. This is from the Keck telescope in Hawaii. These are telescopes equipped with adaptive optics. And this is measuring the heat from a whole series of hotspots. And so putting all of these data sets together, we've been able to catalog all of the volcanoes on Io and quantify their thermal emission. This plot shows 250 volcanoes erupting on, which have been recently or currently erupting on Io. And these range in size from areas of just a few hundred square meters to vast multi-kilometer areas of incandescent material. Rare thermal outbursts actually marked here by squares. These are rare and transient. So the size of these symbols, the larger the symbol, the more energy is coming out. And this is actually on a logarithmic scale. But the heat flow from Io is not even. There are areas where we see a deficit of heat flow and other areas where we see a lot of heat flow. And this isn't really matched very well to the models that we have of either shallow or deep heating. So there's still a lot about the way in which tidal heating is linked to the delivery of lava at the surface. Well, let's take a look at some of these amazing volcanoes. This is a great image obtained by Galileo, which shows a volcano here called Prometheus. This is a volcano which generates a large plume about 100 kilometers high, which lays down this circular deposit which is rich in sulfur dioxide. And in the middle of this plume deposit is a lava flow field, which was emplaced between the Voyager and the Galileo missions in a period of about 16 years. So we can go in and take a closer look at this. Here we have the flows at Prometheus. And for scale, we have an image of Earth's most active basalt volcano. This is Kilauea in Hawaii. And this is the area of flows which was emplaced in about the same time. So the area of flows here is over well over 1,000 square kilometers. And it's actually over 2,000 square kilometers. It's about the area of Rhode Island. And this was emplaced in just 16 years. This is a particularly interesting volcano because what we think is happening here is that lava is coming up at a vent here and then passing through a lava tube system before erupting out at the distal ends of the flows. Very much like what we see in Hawaii. And a logical explanation is lava tube transportation of new lava, which is a great way of transporting lava a great distance without it cooling and solidifying. But along the way, we see these tantalizingly faint, small thermal sources, which could be breakouts onto the surface or skylights, which are holes in the roof of a lava tube. And I'll certainly be coming back and discussing those later. Io's most powerful volcano is in a feature called Loki Patera. And the general consensus is that this is actually a large lava lake. But it's a lava lake 180 kilometers across, so it's probably better to call it a lava sea. It is Io's most persistent, powerful volcano. And we think that it has a very unique way of being resurfaced. We think that what is happening at Loki Patera is that the crust on the lava lake forms with time, and it thickens with time until it gets to a point where the crust starts to sink. And then basically the entire surface of the lava lake is resurfaced by this crust sinking and the sinking crust being replaced with new lava. This is an analysis of a single Galileo NIMS observation that was obtained in 2001, and it shows a temperature map and age map of the surface from the analysis of the data. And what this implies is that this resurfacing wave, if you like, swept around the Patera at a rate of about 1 kilometer a day. So what happens is the Patera resurfaces itself, and then it remains quiescent for a while the crust thickens, and then the crust sinks again. And it's been doing this periodically for decades. Well, in 2015, the Large Binocular Telescope Interferometer, which is on a mountaintop in Arizona, collected this truly astonishing set of observations which shows Europa passing across and eclipsing or occulting Loki Patera. So Loki Patera is here, and this is Europa passing across in front of Io, between Io and the telescope on Earth. And what this means is that as Europa's edge passes across Loki Patera, it covers up the Patera in one direction, and we get this light curve here as light is cut off and heat is cut off. But as Europa uncovers Loki Patera, we get this curve with the limb going in a different direction. And so by fitting these little squiggles in the data set, we created, and this was an effort led by Catherine DeClear, who's now at Caltech, we created the highest spatial resolution map of Loki Patera's surface that's ever been obtained, even including data from spacecraft. We managed to create a map over the entire Patera floor. And fitting this lava lake model to it, and looking at the distribution of temperatures on the surface from which you can infer age, because the older the surface, the cooler it is. The explanation that we came up with for this particular temperature distribution was this. Two resurfacing waves sweeping around the Patera to form this resulting temperature distribution, which was observed by the Large Binocular Telescope Interferometer. And this is something which is consistent with previous observations, and it's a really nice vindication of this lava lake resurfacing model. A more active lava lake on Io is at Pele. And Pele is at the center of this bright red deposit, which is a plume deposit, a plume fallout. It's a plume that's hundreds of kilometers high, and it's led to this deposit on the surface, rich in short-chain sulfur allotropes, about 1,200 kilometers across. And we think that Pele has every appearance of an active overturning lava lake with the plume basically forcing its way up through the middle of the lake and disrupting the surface, revealing high temperature lava. And it's much larger. It's about 38 kilometers across and much larger than its terrestrial equivalents. This is the Kupainaha lava lake in Hawaii. Terrestrially, lava lakes are maybe 10 or 20 up to 100 or 200 meters in diameter. Io's volcanoes, Io's lava lakes seem to be hundreds or even thousands of kilometers, square kilometers in size. Loki Patera itself, Loki Patera has a surface area of over 21,000 square kilometers, which makes it even larger than West Virginia. Io's most powerful eruptions, thermal outbursts, are now known to be caused by large lava fountains gushing forth from long fissures. And these sort of events were actually seen. A couple of them were seen by Galileo. And this is what's happening along this fissure here, and this is the result of saturation, because so much energy was being received by the spacecraft, the detector saturated. And this is a problem that we've come across time and time again with trying to image these very powerful events. We now see these things from Earth-based telescopes. They were actually discovered by Earth-based telescopes back in the 1990s. But we're continuing to discover these. They're quite rare, and they're quite short-lived, but they're very powerful. In 2013, we saw two of these at Rarog and Haino Patere in the southern hemisphere of Io. This is an interesting image because it does show that at short wavelengths, that Loki Patera does not emit a lot of energy. Most of the energy being emitted from Loki is at longer wavelengths. And what that tells us is that, generally speaking, Loki is a relatively cool surface compared with what we see at these outbursts. So for the purposes of determining eruption temperature of the lava, Loki Patera may not be our best candidate, whereas something like Pele, where we have overturning lava lakes, an overturning lava lake on a much shorter time scale is a better candidate. So by looking at all of this data and doing a lot of modeling, and we've come up with a classification schema where we can identify the characteristic thermal fingerprints of different styles of volcanic activity. The most powerful eruptions are these outburst eruptions, these large lava fountain events. We have the Pele overturning lava lake right here. And at the bottom, we have these small but powerful lava tube skylights. These are small but very high temperature. I'll be talking more about these later. So Io is a fascinating body in terms of it was the first body where we really did see active resurfacing processes. But the Voyager, Cassini, and Galileo missions have shown that there are many other satellites in the solar system which have this dynamic, evolving structure. For example, we have Enceladus, which is one of the moons of Saturn, which has water plumes erupting from the South Polar region. And we have Titan and the Jovian satellite Europa, which have geologically young surfaces. But Io, and all of these bodies are to some extent tidally heated, but Io is the most tidally heated body in the solar system, and it's probably the best place to study this the extreme limits of this process. So the big picture as it stands is that we know that Io and Europa are tidally bound together. But how much heating is, and where this heating is taking place within the satellites is not really well constrained. But as tidal heating is most pronounced at Io, it's really knowing Io's interior condition that gives us some insight into further constraining how much heat is being input into Europa. So on Io, it's the eruption temperature of Io's lavas which could be diagnostic of interior conditions. And so looking to Io's volcanoes to get these data is what we need to do as a way of constraining the interior state of Io. So the big question in the wake of the Galileo mission regarding volcanism on Io is, what is the composition of the silicate lavas on Io? This reflects what's happening inside. We know that Io's volcanism is dominated by low viscosity, quite fluid lava, like basalt. Basalt erupts at about 1140 centigrade. And this is the most common volcanic material in the solar system. But it's also possible that with on Io that we have a type of lava called ultramafic lava, one of which is a komatiite, and this erupts at hundreds of centigrade higher temperatures. And this is interesting to us because ultramafic lavas were once common on Earth in Earth's distant past, and it might have been a time when this reflected a hotter mantle in the Earth. So if ultramafic lavas are indeed erupting on Io would truly be a window back into Earth's geological past. Now, the hotter the lava, the more interior heating is taking place, and the more liquid the interior. But it's very difficult to tell the difference between ultramafic and basaltic lavas by temperature alone. Firstly, we have to look at a very narrow part of the thermal emission spectrum. And secondly, the problem here, and this is something that has bedeviled efforts to do this with remote sensing, is that we're trying to tell the difference between a lava that erupts at a very high temperature and something that erupts at a very, very high temperature. So komatiites, it only takes a couple of seconds for a komatiite erupting at this temperature of, say, 1850 Kelvin to cool down to the temperature at which basalt erupts. And so it's very difficult to tell one from the other. And if you're going to go to Io and look at styles of volcanic activity, to try and do this, only certain styles of volcanic activity will do. And the first is lava fountains. And this is something we have to get pretty close to and image, say, the base of the lava fountain before the lava that's gushing out of the ground can cool too much. And the problem with this is that these are relatively rare and it's impossible to predict where these are going to happen. Lava tube skylights are a particularly good candidate for doing this because they're small. You have a very high temperature gradient between the lava tube skylight and the surrounding area, so these things stick out very well. And the temperatures inside are very close to eruption temperature because the lava tube itself is highly insulating. And then we have lava lakes. And what we're interested about in lava lakes is the fountaining that takes place, because it's the fountaining events that reveal the lava at its highest temperatures. So I've been traveling around and looking at lava lakes and taking models of volcanic activity to understand how best to measure lava eruption temperature. So a few years ago, I went to Erebus in Antarctica. These are observations obtained by a satellite in Earth orbit, Earth Observing 1. And this is a visible image And this is an infrared image, and we can see the lava lake here with a smaller pit. And I'm actually standing in a pixel about here as this was taken. And here I am at about 13,000 feet on Mount Erebus. And it's a bright, sunny summer day. And the temperature, the ambient temperature, without wind chill, is about minus 40 centigrade. And at the summit, this is our camp. This is at about 11,000 feet. This is the summit of Erebus. And at the summit, there's a crater about 600 meters across, and it's about 250 meters deep. And in that crater, there is an active lava lake of a lava called phonolite. It's quite a rare composition. And this is the lava lake itself. It's about 38 meters across, and quite one of the most extraordinary things I've ever seen. And I took down a thermal imager, a FLIR thermal imager with me, and this is the data, some of the data that was collected. And what we see here is that lava is welling up at the center of the lake, forming a crust which then moves laterally, and then the lava goes down at the edges. And this has been circulating around between the surface and the deep-seated magma chamber about 3 or 4 kilometers down. So this was a great test of a model that was created to determine the temperature and area distribution. And this is just a cartoon of that model. We have lava rising up, spreading, and then sinking. So there is a mathematically defined progression in cooling across the surface of the lake. And if you integrate over that, and then you can compare that with the data, this is what we got. And this was great. This was a great pleasure to me to actually do this, because the model fit to the data. We produced the thermal emission as a function of wavelength, the total power emitted, and the area of the lava lake just down to a few percent. So this is very gratifying. There was a slight discrepancy in the fit between the model down here, and that is just basically because the model used a basaltic composition, and it was only the lava eruption temperature that was different, and that's why there's a slight gap here. So it looks like the model is actually very sensitive to temperature, and this improves our confidence of fitting data that we get from spacecraft. Now, the resurfacing mechanism at Erebus was generally very quiescent. But when I was there in 2005, every 6 to 9 hours, the lava lake would resurface itself like this. I have to do my own special effects. But that's what it sounded like. It was pretty impressive when this thing blew. So yeah, this is a Strombolian eruption, and it basically throws out lava bombs up to 3/4 of a kilometer. So you've got to be careful. Okay, all the bad acting aside, the guy under the rock, his name's Alexander Gerst, and at the time he was a graduate student at the University of Hamburg, and now he's an astronaut in the European Space Agency Astronaut Corps, and he's already spent one tour on the International Space Station, and he's mission commander on a mission that's going to be launched in 2018. Well done, Alexander. So for the results from the field trip to Mount Erebus and all the data analysis is that we see that the lava lake thermal signatures, the characteristic thermal signature of a lava lake on Earth and its contemporaries on Io are actually pretty similar. The model fits used to interpret the Io data. The model was actually developed to interpret Io data. Actually works really well on terrestrial data. So that's a good test. And the analysis appears to be sensitive to eruption temperatures, which is important. So this is all very well at Erebus, but how do things look with a better analog for Io? And so a few years later, actually I was asked to go out to this volcano in Africa, the Erta Ale volcano in the Danakil Depression, in the Afar region of Ethiopia, by the BBC, who were filming a series called Wonders of the Solar System. I was obviously a wonder of the solar system, and so they wanted to talk to me about it out there. I jumped at the chance. Erta Ale is located at the northern end of the East African Rift System. This is where Africa is pulling itself apart. And it's a basalt lava lake. And here it is. In 2009, it was about 55 meters across. There was a lot of vigorous churning around at the edges and the occasional lava fountain in the middle, and it's one of the most extraordinary things that I've ever seen. And so here I am on the summit of Erta Ale on a bright, sunny summer day, and the ambient temperature is 133 Fahrenheit. It's 56 centigrade, so it's not surprising I look a little pink. Again, with a thermal image. These lava lakes tend to be in these really, extreme environments. Here I am again with another thermal imager. And this is an hour in the life of the lava lake, compressed down into about 10 seconds time lapse. And what I'd like to point out is a small lava fountain just about here. There it goes. This is where the crust is being disrupted and areas at very high temperature are being revealed. And that's what we're interested in. So I took a look at these data to determine what the effect would be of any kind of delay in getting data at different wavelengths. A traditional way for spacecraft, like Voyager, spacecraft images to work is you take an image of the surface through one filter, you move a filter wheel, you take another image through another filter wheel, through another filter on the wheel, you move the filter again, you take another image, then you combine those images together and you get a color image. That's fine for planetary surfaces, but where we have something that is changing rapidly because it's actually cooling very fast, what is the effect of that when you try this experiment again? And this is what we found, that with even a second delay in taking data at different wavelengths, we got these massive, these massive changes in derived temperature, which really does make it very difficult to have any confidence in an actual temperature derivation. But when you cut the difference in time down to a fraction of a second, we get a much smaller amount of variation. Of course, this would be a flat line if the data were obtained simultaneously. So what we found from Erta Ale is that that areas at target temperatures change so rapidly that observations have to be obtained very fast, and ideally simultaneously at different wavelengths. Now, with Galileo data, we tried deriving temperatures from Galileo data by combining different SSI frames and combining NIMS data with SSI data. And we found that with seconds and minutes between observations, it damages our confidence in the results because the target that we're looking at was probably changing in that time. Now, this is not a criticism of Galileo by any means of the imagination, because the instruments of Galileo are simply not designed to do what we'd like to do with the next mission. We see as far as we do because we stand on the shoulders of giants. So this is not a criticism of Galileo at all. And the upshot of this is that observations have to be obtained in a fraction of a second. So we're really getting close now to what we need to overcome these problems. We have a very good handle on the derivation of the style of volcanic activity from studying volcanoes on Earth and studying volcanoes on Io. On that note, there was a paper published just last year where we quantified the thermal emission that you would get from a lava tube skylight for both basalt and ultramafic compositions. So now we have the distinctive thermal fingerprints for both of these compositions to help us analyze any new spacecraft data that we might get of volcanism on Io, or this style of volcanism on Io. We have a very good handle on the rapid cooling of new lava. We know how the process works, and we know some of the problems that have to be overcome with that. And with lava fountains and with fountaining in lava lakes, there is still the problem of the unpredictable magnitude of thermal emission, because if too much radiance is captured by the detector, it will saturate, and then the data are no good for deriving eruption temperature. But there's a number of ways of doing it, and here's one. This is an effort being led by Alex Soibel here at JPL. It uses something called the Hotbird detector, which was invented here at JPL, and an integrated circuit that was invented at MIT Lincoln Labs. And it splits the signal coming in. It obtains data simultaneously at multiple wavelengths. For our purposes, the detector and the circuit are non-saturating, so there's no saturation effect, and it's got a fast integration time. So this is just one approach that can be used to get the data that we need to measure lava eruption temperatures on Io accurately. So now we really do have all of the pieces of the puzzle. We can identify different eruption styles on Io. We can understand, and we have a good understanding of how these different eruptions behave thermally and temporally. So we really do know what observations to make. We have some designs for instruments to collect the data, and we have models that can be used to interpret the data once obtained. And now the only thing we're missing now are new data. So the unlocking of Io's secrets has been an incremental process. The Voyager spacecraft discovered that Io was volcanically active, but it did so with instruments that were not designed for looking at any kind of silicate volcanism. This was completely unthought of when the instruments were designed in the first place. Galileo discovered that silicate volcanism was the dominant form of volcanism on Io. And now the question is, what is the actual composition of the lavas? Is it uniform across Io, or are there different compositions being erupted in different places which reflect the depth of origin of these lavas? Are they hot, or are they very hot? So really, a new mission is needed to get back to Io. And there have been different missions proposed over the years. This is one that was proposed a couple of years ago. It may be proposed again by Alfred McEwen at the University of Arizona. It's called the Io Volcano Observer, or IVO. IVO and other missions like it will be the first mission sent back to Io dedicated to studying Io's volcanoes and the interior processes, with instruments designed specifically to overcome the problems that are inherent in trying to understand what's happening on Io, to finally nail down eruption temperatures, constrain interior state, and then this can be applied also to Europa. So in conclusion, we really truly are living in a golden age of exploration. We know the big Io questions can be answered. And to a volcanologist, Io is a truly amazing place. It's a window into Earth's past. It's key to understanding Jupiter's satellites. It's a volcanologist's paradise. Thank you very much. If anyone has any questions, please use the microphone set up in the middle of the room.
Hi, great presentation. I had a quick question with regards to the potential for an atmosphere on Io. So is there any indication there was an atmosphere, or is there an atmosphere? Will there be an atmosphere in the future?
There is a very, very thin atmosphere of sulfur dioxide which appears to freeze out at night. It's not as thick as Earth's atmosphere. We're talking about something that is just a tiny fraction of a bar. And it's basically sulfur dioxide that's generated from the volcanoes themselves. and by lava flowing across the surface and melting and remobilizing sulfur dioxide gas and sulfur on the surface, remobilizing ices.
Hi, I'm just wondering if you have any plans to visit more volcanoes or if any specific ones you'd like to go to.
I try to visit as many volcanoes as I can. I made my first trip to Etna this year, which is very exciting. That's where I encountered the sort of the mantra of the volcanologist, which was, you should have stayed an extra couple of days. Usually it's you should have been here last week. In this case, I left a couple of days before it erupted quite spectacularly. I would like to go back to Urte Aarle with new equipment. I'd like to go. I spend a lot of time at Kilauea because Kilauea is convenient, it's relatively close, and it's a great analog for a lot of the styles of volcanic activity that we see on Io. So it's a great test bed, and it's a great learning experience to go out and watch the eruptions take place. Yeah.
Hi. I understand there are about 400 active volcanoes on Io, contributing to the ejecta and also to the plasmatoris. And my question is, are there any dormant volcanoes on Io, or do you know of any that are going dormant?
We've identified 250 locations where there's been active or recent volcanism, and there are, as you quite correctly say, there are about 400 sites on Io which look like dormant. There are 400 sites on Io which have the appearance of past activity as well as the current activity. So yes, there are many sites on Io which look as if they once were volcanic but don't appear to be volcanic now. I don't think that there's been any correlation between where the activity is taking place now and where it seemed to have taken place at some other time. So there may be something hidden in those data which reflect a shift in maybe regional volcanism. But no, I can't say anything definitive about that right now.
Thank you.
Yeah. Welcome.
So first of all, thank you very much for your presentation. It's been very eye-opening.
Thank you.
Pun not intended, I promise.
Good.
So my question is, have we been able to detect a magnetic field around Io? And if not, what's the theory for what's missing in development for that magnetic field?
I'm not sure the answer. The Galileo magnetometer did some measurements as it went past Io, which did infer that there was through magnetic induction that there was a global magma ocean. I'm not sure about the strength and size of Io's magnetic field.
Thank you very much.
Hi. My question is, do we have an understanding of the mechanism for emplacement of the magma at the surface? Is there some sort of tectonism going on that is a mechanism for that?
Right. We don't think there's any sort of global tectonics the way we see global tectonics on Earth. Instead, we have a heat pipe mechanism where lava, well, magma works its way up from the top of the lithosphere to the surface. What helps it get there seems to be a trend for large faults in the crust, providing planes of weakness and reducing stress, horizontal stress, which provides pathways for lava to get to the surface. And the problem with Io is it's being resurfaced so fast that the crust is getting compressed down. And so very large horizontal stresses build up. And these stresses are relieved by large crustal blocks tilting and by faulting in other areas. And these seem to provide pathways for lava to get to the surface. So the thick crust seems to be fractured sufficiently to allow the passage of lava passage of magma to the surface in many locations. But there are no plate tectonics like what we see on Earth.
There's fracturing, but there's no
There's fracturing,
movement.
but there's no subduction,
Yeah.
and there's no sort of, there don't seem to be any spreading centers.
Okay, thank you.
Hi, you may not be able to answer this, but I can't help but wondering if the Europa Clipper might be carrying an instrument that perhaps in an extended mission could collect some of the data that you're looking for from Io.
Yeah, we're still trying to figure out what to look at on Europa with Europa Clipper. And Europa Clipper is not going to make any close passes to Io because Io is deep in Jupiter's radiation belt. So I think the best chance for understanding Io's volcanism is with a dedicated Io mission.
Two questions. The second one, I guess, was already answered, that we're not going to, Europa Clipper isn't going to help here. So if the energy for all this activity is coming from the tidal forces between the different satellites, is there enough energy in that orbital motion to power the heat for the whole lifetime of the solar system and for a billion years in the future?
It looks like Io, one of the theories about Io and Europa and Ganymede is that they move in and out of this orbital resonance. So what we see is a complicated byplay between orbital dynamics and the interior structure of Io, Europa, and Ganymede. So it looks like on a scale of maybe hundreds of millions of years, Io and the other satellites may move in and out of the resonance, which would actually cut off volcanism on Io. So it might be that Io is going through, at the moment, a very high level of volcanic activity because it's at a peak in this scale. We don't really know, but that's important because you get to the point where Io's interior is so fluid that the tidal forces end up moving, just basically moving the fluid around, and volcanism will actually come to an end once it moves out of the resonance. Then once it's out of the resonance and the tidal forces can get a grip on a solid Io again, it will move back into resonance and volcanism will start again. And this might happen so quickly that we get total mixing or total melting of the interior, so that we go back to basalt, we go back to possibly ultramafic material. It's a conveyor belt of volcanic activity that moves so fast that we don't get highly evolved melts on Io. We don't get highly silica content lavas like we see on Earth. We don't get a secondary crust forming or tertiary crust forming. So it might be that Io is heated back to an extent where it's a primitive interior composition, which is why it's interesting, because that would reflect the early Earth.
Very interesting. Thank you.
Great talk, Ashley. I have a question and a comment. The question is, given all of the modeling that you've done, and now it looks like we also see cryovolcanism, as you mentioned previously, in places like Titan, Enceladus, and Triton, to what extent can you apply the models that you've developed for sort of magma to cryomagmas? And then the comment is that today does happen to be the 14th anniversary of when Galileo did its plunge into Jupiter's atmosphere. So it's quite appropriate, I think, that you gave this talk tonight.
Right. Yes. The physics of the eruption and cooling and emplacement of cryolavas, it's very similar to the modeling that I've been doing. Basically, it's just the physical inputs, values that are changing. So yes, and I've looked at the emplacement of cryolavas on Titan and some of the effects on Enceladus as well. Okay, we have some questions. Questions from the internet. So, Finding Freedom asks, Could debris and particles from Io's volcanic eruptions damage spacecraft orbiting or flying by the moon? The answer is yes, they could. Galileo itself had its orbit, its orbital trajectory changed to avoid a large plume, and ended up running into another plume. That's just the way it is. But it is possible to damage a spacecraft, and that really depends on what kind of plume is erupting, how big it is, how much material has been incorporated into it. But your spacecraft is basically flying through this at about 6 or 7 kilometers a second, so even small particles can do damage. Alex asks, do the volcanoes act differently being directly exposed to the vacuum of space? And that's a good question. On Earth, Old Faithful goes up about 30 or 40 meters. On Io, you put under the same eruption conditions, because you are erupting into a vacuum and because gravity is lower. If it was just gravity lower, the plume would be six times higher. But because you're erupting into a vacuum, you get a much more expansion, you get much more bang for the buck, and Old Faithful will be 38 kilometers high. So erupting into a vacuum means that if there's any gas exsolving from the lava, you tend to erupt much higher velocities than on Earth, where things are a little controlled by atmospheric pressure. And finally, Paige asks, is there topographical information about Io's lava lakes? I'd be curious to see the heights and depths of Loki Patera. We have a pretty sparse data set where there's high enough resolution to make any kinds of measurements of lava flows and the lava lake. The lava lake just seems to be completely flat. We see specular reflection off the surface, which kind of enhances the idea that it is in fact a lava lake. There is only one measurement, direct measurement of the thickness of a lava flow on Io, and that is about 10 meters thick at a location called Palan Patera, where there was a big eruption in 1997 which emplaced really large lava flows, which in the space of a few months covered 5,600 square kilometers. And these flows ended up about 10 meters thick, about 30 feet. Okay, that's the last question. Does anyone else have any questions? Oh, thank you very much for coming tonight. Thank you.